problem, any optimization problem that has a polynomial time algorithm, you can solve in polynomial time using linear programming, it turns out. And this is an example of that. This is called a network flow program and a problem. And the idea, to remind you, is you've got S and T. So you think of S as the oil fields and T as the oil tanker port. And you can produce as much oil as you want. You can produce oil as much as you need. And the idea is you want to ship as much oil as possible from S to T on these pipelines. The pipelines are one direction, they have a capacity. So obviously, the most you could ship out of S is 10, right? 10 units per day or hour or whatever. Because there are only 3 pipelines and their combined capacity is 10. All right. But if you did that, actually put 10 units on the pipeline, you'd run into trouble. Because you'd be sending 3 to B and 3 to A. Those 3 you sent to B have to be sent up to A, and now A can't deal with 6 units coming in because it's only got 2 units going out. So what we want to find is the maximum amount that we can either suck into S or send out of T to the waiting oil tankers without overwhelming the pipeline capacity to any of these pumping stations in the middle. So that's the setup. What's the maximum amount of oil that we can send through the system? Okay, the answer is 7, it turns out. But let's write a linear program to do that. So here's the preview. There's our graph. And this is a solution. This shows how much you actually ship. So one solution is to send 2 units here and 1 unit here. And then send nothing up there, but send this one over here. And so forth. That shows a solution. And you can see 7 units are leaving, 7 units are entering. And at every point, we're putting 4, 5 in to C, and then 5 is out. We have that property is reserved throughout all the 4 or 5 pumping stations in the middle. How can we cast this as a linear program? What are the variables? What are the constraints? What's the objective function? So let's start with this. Is this a minimization problem or a maximization problem? Okay, we're trying to maximize the flow. All right. What would be an objective? What variables do we need? Yeah.
Do we need a capacity in and capacity out for each vertex?
We will, but those aren't variables. It's more of a constraint. Yeah.
So are you talking about the variables that are going into our linear program?
Yeah, the variables in our linear program.
Have all the edges.
Okay. So there are various ways to write the linear program. And I guess what I should have said about your suggestion is the way I have in mind, that wouldn't be a variable. So we have however many edges. What if we had a variable for each? So let our variables be like CE, SB, BA, and so on. So each directed edge would be a variable. What would the objective function be? What are we trying to maximize?
The oil shipped from S to T.
Say again?
The oil shipped from S to T.
Okay, but how do we express that in terms of these variables I just said? Go ahead, Anthony.
DT plus ET.
Okay, one way would be to maximize DT plus ET, right? So DT is the amount of oil that's actually shipped, as opposed to the capacity. So don't think of DT as being the capacity edge. What we're solving for DT, where DT would be the amount we actually ship, or we actually send down the pipe. So we want to maximize DT plus ET. That's the amount going out. What else could we maximize? Yeah.
The amount leaving S.
Right, so we could maximize SA plus SB plus SC. Either way ought to work. But this is subject to constraints. So what are the constraints that we have to obey? These variables can't take on arbitrary values. What's a constraint we're going to have to impose, say, on the edge SA? What's that?
Max of 2.
Well, be sure and look at that one up there.
Oh, max.
Max of 3. You can't send, remember, this is the answer. We're working from that graph right there. So SA has to be less than or equal to 3 because that's the capacity of the pipe. All right? And while we're at it, can you think of another bound on SA? Yeah.
SA plus SB equals 80.
You saying SA plus
SB.
equals what?
BA equals 80.
Where's the 80 come from?
The outgoing of
80, not the number 80.
Oh, right. Okay. Let me get back to that suggestion. There's a simpler constraint we can put just on the SA. Yeah.
Can you ship negative oil?
Right. You can't ship negative oil, so SA has to be greater than 0. So all these edges have to be greater than equal to 0. They have to be less than or equal to their stated capacity up there. And now back to his. Look at node A. What has to be true there is that SA plus BA must equal AD. The amount going into A has to be equal to the amount leaving. And you can construct a constraint like that for every vertex, for every interior vertex, for every pumping station. Yeah.
Why equal and not equal to or less?
Because he asked why not, why equal, why not less than or equal to? Because these pumping stations, there can't be oil pooling up, right? Any oil that comes in has to be sent out immediately. And the other way around is you can't send out more oil than you're getting, which is probably more pertinent to your suggestion. So, you know, if we're sending in, say, 2 units to A, but we only, let's say that we'll do 1, we're only sending out 1, that's bad because oil is accumulating. Or the other way around, if we're sending none in, we can't be sending 2 out. It has to be a balance. That's the constraint. So, there's our program. Right? So I chose to maximize the input. So we maximize SA plus SB plus SC. Here's our constraints. This is where this says all the edges, their values must be positive. They must be less or equal to their capacity. And these are the 5 constraints of pumping stations. Oil in must equal oil out. So you just take that and feed it to a problem, an LP solver, and it solves it and produces the solution we saw on the last page. So it tells you the maximum value the objective can have, which is 7, but it also tells you the value of each variable, which is the amount of oil to put on each pipe. Yeah?
So what does the feasible region look like?
Okay, he asked what, he's trying to visualize the feasible region. Okay, what can we say about the feasible region?
Convex.
Well, yeah, it's always convex. Is this a 2-dimensional problem? Yeah?
It's n-dimensional in n of how many edges we have?
Yeah. So how many edges are there?
11.
So it's an 11-dimensional feasible region.
Can we plot it with,
So I can't help you with visualizing it.
Can we break it down and plot it with like with 4 3-dimensional problems?
Well, you could take a slice through it, I guess, with a plane and look at various views. But it literally is an 11-dimensional polyhedron. It's probably, you know, I won't belabor it. It'd be hard to sketch. But mathematically, it's just, you know, it works the same as a 2-dimensional thing. You just, you know, the optimal value appears on one of the vertices, and the problem is to figure out which one. And I guess the reason you don't see a problem like this when it's being introduced, as opposed to making chocolate bars, is the 2-dimensional problem works a lot better for graphing, such as what you're doing in the current assignment. Okay? So that's kind of interesting there. And I'm not claiming that this is the most efficient way to solve the network flow problem. There are specialized algorithms for this, like for any other kind of graph problem, but this is a way, and it runs in polynomial time. Can be solved in polynomial time, I should say. Okay? So now, done with that one, let's look at this problem here. This is a problem you're familiar with. that we know we can solve with, say, Dijkstra's algorithm. And, but we're going to try to write a linear program for this. All right? So think about it for a minute. How can we describe, how can we come up with variables and objective function and constraints in order to solve this? It's a little tricky. What are we trying to maximize or minimize? What are we trying to, what are the constraints? Got an idea?
Idea of when you make an objective function,
Okay, so what would be the objective function?
something like a plus b plus c plus d must be the min of all the edges added together or something.
Okay, so it's certainly going to have something to do with the edges. All right, well let's explore here for a second. All right, so I'm going to have my variables be a, b, c, and d. In this case, a is going to be the minimum distance. You know, think of a as the distance in a minimum. Okay, we're trying to find a tree. It's basically trying to find a spanning tree rooted a that has a property that is the smallest possible, shortest paths tree. So a is the distance from a to a in a shortest paths tree. B is the distance from A to B in a shortest path tree, and so on. So we're trying to, we want A, B, C, and we want to solve for A, B, C, and D, basically. So in a solution, what would A be? Trying to find the shortest path tree rooted at A. So when we finally run the program, what will A be?
0.
A will be 0. What will B be?
5.
4.
4, because the 3 to 1, A to C to B is the smallest, so it's 4. C will ultimately be 3, and D will ultimately be 6. Okay, so we're trying to solve that. So we'll let those be our variables. Now let's try to write a linear program, an objective function and constraints. So what constraints can you put on A, or let's just take C, for example. What constraints can you put on C? But B is a better one to think about. What constraints can you put on B?
It has to be at least one of the edges, any one of the edges in the route has to be at least that size or greater. In the shortest, in the path that we know, it has to be that short path.
Okay, I think you're going in the right direction. Yeah.
So the b has to be a sum of a and c, but not b.
Well, no, you don't look at the thing and solve it and then make the constraints. Clearly, we could look at this and say, okay, here's my constraints. A equals 0, B equals 4, C equals 3, D equals 6, right? I can just look at it, solve the problem, write the solution down, and call that my constraints, and that'd be fine. But that's not a general way to approach solving it for any arbitrary tree. Yeah?
B is equal to the min of...
Well, you can't do min. You got the right idea. You just can't say min. You can't put min in a linear program. Just linear inequalities. But what were you trying to... I shouldn't have interrupted you, though.
Oh, well, I was going to say, B is equal to the min of either A plus the edge AB, or C plus the edge CB.
Okay. So B has to be... B can't be bigger than A plus 5, right? And B can't be bigger than C plus 1. Okay? How can we express that without a min? Yeah?
You could have two separate constraints.
Right, you just put two constraints. One constraint is B is less than or equal to A plus 5. And the other constraint is that B is less than or equal to C plus 1. So for every edge coming into a vertex, you've got a constraint of that form. It's just saying that the minimum distance to B can't be bigger than the minimum distance to C plus the 1 it would take to get from C to B. and the minimum distance to B cannot be greater than distance to A plus the 5 that it takes to get the edge in there. Okay? So we could add 2 constraints for B. What about for C? There are actually 2, because there's this possibility. So there are 2 edges in, so there'd be those constraints. And then what about for D?
Just one.
The 1 constraint. Now what can we do with A?
Just set it to 0.
A zero.
Yeah, so for the root, we know the distance to the root's got to be 0. We're assuming there are negative edges. So A has to be, maybe just say A equals 0. Okay, so we've got bounds above on B, C, and D. What else could we say? What would be a bound from below? Yeah, they're all, we know, since there are no negative edges, we know that everything's greater than or equal to 0. Great, so those constraints sort of describe our problem. But what are we trying to minimize or maximize? Yeah?
The sum of A through D.
Okay, so we want to do what? Minimize or maximize A plus B plus C plus D. A plus B plus C plus D would be the total cost of the minimum spanning tree. Right? Not the minimum spanning tree, the shortest path tree. That's what we're trying to minimize. So do we try to minimize A plus B plus C plus D, or maximize A plus B plus C plus D? How many think we minimize it? How many think we maximize it? Yeah, we want to maximize it. Now, that seems kind of weird because it's minimum spanning tree. What would happen if we try to minimize A plus B plus C plus D?
We just did A the whole time.
Well, what's the minimum value A, B, C, and D can have with our constraints? 0. What if we set A, B, C, and D to 0? Okay, they'd all be greater than or equal to 0. And B would be less than or equal to A plus 5. And B would be less than or equal to C plus 1. So if we tried to minimize that objective function, we'd end up with 0 for everything. But maximizing seems crazy because this is a minimum spanning tree. But here's how to think about it.
Shortest path tree.
Okay. So whenever I say minimum spanning tree today, just mentally map it to the shortest path tree. For some reason, I got that on my mind. All right. Imagine this exercise. So for this exercise to work, we're going to have to think of it as an undirected graph. So imagine that was an undirected graph. Let's make a physical model of the situation. In other words, let's take, imagine taking 4 rings and some string. And we'll put a string of link, we'll make a 5-inch string between A and B. And we'll make a 3-inch string between A and C and so on. Now, if you wanted to find the shortest path between A and D, what would you do? Right, you take the A ring, the D ring, and pull them as far apart as possible. And what would our contraption look like at that point?
The shortest path would be.
Yeah.
Right, so
C to B.
So it would be all stretched out. The A to C string would be tight, the C to B string would be tight, and the B to C, well, B to D.
AC,
Anyway, that's the path right there. So it's a little tricky because I got to remove those arrowheads. So let's see. The shortest path from A to D, if we remove the arrowheads, would be 7, A, C, D, or it'd still be 6, A, C, B, D. So that would all be tight. And then the other strings would be hanging limp. All right, or if we want the shortest path from A to B, we would take the A ring, the B ring, hold them tight, and you would have the A to C to B string would be tight, strings would be tight, the others would be hanging limp. Does that make physical sense to you? But what are we doing when we pull them as far apart as possible?
Maximizing.
We're maximizing. Subject to what constraints?
The lengths of the string.
The lengths of the strings can't be exceeded. It's exactly our linear program. So we have to maximize. And the reason another way to think about it is we got to maximize because whatever path we choose as the shortest, we've got to use all if we decide to use the path from A to C, we've got to use all of A to C. We can't use part of A to C, or it's not really a solution. So yeah, it's kind of weird to contemplate that you want to maximize the objective function. But anyway, there it is. And there's a solution. And you feed this to LP SOP, that's what you get. The totals, the sum of all the path lengths is 13. And that's the distance in the tree, in the shortest path tree from A. So sometimes it can be kind of tricky to express a solution like this. Yeah.
Does the ordering of our inequalities matter, or how does the linearization program deal with like the different possible values?
Yeah, the order doesn't matter. Just think if they're all ANDed. Just all the constraints have to be observed, and so it just finds the best it can do subject to those constraints. Okay. Any other questions about this? We're going to revisit this. It turns out that you can, under certain conditions, which we'll just see, if there is a linear program with an objective function that you maximize, there is another linear program for the same problem with an objective function that you minimize. That's called the dual. So linear programs come in duals. And so we could, if we used a different set of variables, if you use the variables that represent different things other than what we chose here, we could write a linear program to solve this that was a minimization problem. The other cool thing about it is you can actually calculate the dual. So I'll explain about duals for a while, and then we will turn around and see what the dual of this is. See how you can express this as a minimization problem. Okay, so this is the example that we started with, where we have two kinds of chocolate, and there's some simple constraints. So our objective function was to maximize profit. So x1 and x2 was the amount of each kind of chocolate that you sell, subject to those constraints, and that was our solution. So we're sort of going back to our very simple linear program. All right. Now, suppose someone just said, this is the solution. How could you check it? How could you verify that was a solution? What could you do? Okay.
Resolve it and then see.
Well, I don't mean to. Yeah, you could type it into your LP solver and make sure you got the same answer. But I mean, just by looking at it on the face here, what can you check? Yeah.
If you wanted to brute force it, you could do every possible permutation of x1 and x2.
Yeah. Okay, that's not what I'm after.
Okay.
All right. Yeah.
Just verify that the solutions match the constraints.
Yeah, you could. So you can take. The claim is that x1 and x2 take on these values. You get that. So one thing you can check is, okay, x1 is 100. Is 100 greater than or equal to 0? Check. Is 300 greater than or equal to 0? Check. Is 100 less than 200? Yes. Is 300 less than or equal to 300? Yes. Is the sum of those two things less than or equal to 400? Yes. If you plug 100 and 300 into here, you get 1900. Okay, that's the kind of checking I'm talking about. That's easy to do. But what's the one thing we haven't managed to verify? Yeah.
But it is the maximum.
Right, that this really is optimal. Maybe there's another solution that's better. All right, and what we're going to see now is how to verify that. All right, so it's easy to check that stuff. That's what we just said. We've got constraints. We can combine them. Let me show you what I mean. Let's take this x less than or equal to 200 constraint and this constraint. Now, what have I done up there?
You plugged in the maximums for x1 and x2.
Okay, so this is my objective, right? It's 1x1 plus 6x2. So the objective was 1x plus, oh yeah. All right, that's the objective right there. Okay? And so I know that x1 has to be less than or equal to 200. x2 has to be less than or equal to 300. Yep.
So you're saying kind of, if you only had to consider these two constraints on x1 and x2, what would be the maximum profit?
Well, no, this isn't computing max, this is putting an upper bound on how big the objective can be.
Okay.
Okay? So it's saying that those two constraints in yellow combined together tell you that the biggest x1 plus 6x2 can be is 2,000. Because x1 cannot be as big as 200. x2 can be as big as 300. So if x1 is 200 and x2 is 300, which are both allowed by those constraints, then x1 plus 6x2 is 2,000. So by just taking constraints like that and combining them according to the objective, you can get an upper bound. So we know that the objective function couldn't possibly become bigger than 2,000, simply because of those two bounds on x1 and x2. Yeah?
Yeah, but why aren't you considering that x1 plus x2 has to be less than 400?
Okay, so we asked, what about the other constraints? All right? We'll get there. But at this point, remember our problem, what we're trying to do is verify this. So now we know that, okay, if that's wrong, it can't be bad wrong. Because if we maximize this objective, we can't possibly get bigger than 2,000. Just because, if you just look at those two constraints, you can tell you can't get bigger than 2,000. All right, let's try again. Let's look at this constraint for x2 and that constraint here.
I think the 5 is a typo.
That's what I'm looking at too.
Yeah. It should be 6.
No, that's right.
Is it?
Yeah.
Yeah. Oh, yeah.
It's right because we're trying to get 1x1 and 6x2s.
Yes.
And we get 5x2s over here and we get 1x2s over here.
There.
And
Yeah.
1x1. So essentially, if we take that sum right there, we get this inequality right here. This inequality over here reduces that inequality over here. So our goal is always to combine inequalities in a linear fashion so that you can rearrange terms to get the objective function on the left and a value on the right. Okay? So since we know that x2 has to be less than or equal to 300 and x1 plus x2 is less than or equal to 400, if you just multiply through, add left-hand sides and right-hand sides, you get this. And what does that tell you?
Joe,
Yeah?
shouldn't that be 500? x1 plus x2 is less than or equal to 500?
No.
400.
Oh, okay, I didn't see that.
Oh,
And if you add two inequalities, you get an inequality. So we just do a linear combination of inequalities, and that gives us this. And that's saying that the objective function cannot be bigger than 1900. And we know it's possible to hit 1900. So there's our verification. Yeah?
It seems less like verification and more just like resolving it.
Okay, so he's saying so basically, you're right.
Okay.
Where did those coefficients, 5 and 1, come from? How do we decide to use those two inequalities and suppose it's two other inequalities? All right? So he's saying we're essentially resolving the problem from a different perspective.
so could we do this to solve our linear?
Okay, well, so yeah, well, you'll see what this has to do with, with the problem we started with. Okay? So it is possible. You take a linear program and you want to verify it. There will be a way to take the inequalities that went in and multiply them by constants and add them together and rearrange so that you get an upper bound on the objective, or a lower bound if it's a minimization problem. And if you're clever enough, you can get the exact bound you need. it's one thing to fish around and find the right constraints to combine when there's 2 variables and 5 constraints. But what if there's hundreds of variables and thousands of constraints? That'd be a much tougher exercise. So how can we automate the process? Yeah?
Is it like every permutation of the variables?
You said every permutation of the variables? No, it's not that complicated. Let's see here. Let's do it symbolically. What we're after is we want to multiply, I'm not going to worry about these constraints because we're trying to come at it from above. So I'm going to multiply each of those upper bound constraints by something. And we want to multiply by things so that it'll add up to what? So I've multiplied and rearranged my inequality. What property do we want the thing right here to have? We're trying to put an upper bound on this objective function. What property did the 1 and the 6? When we chose the 1 and the 6, why did we choose them? Why do we use 5 and 1 in the next one? Yeah.
So we want y1 plus y3 to equal 1 and y2 plus y3 to equal 6.
Right. We want this right here to look like the objective function, x1 plus 6x2. Up there, we chose 1 and 6 so that we would get x1 plus 6x2 on the left-hand side of the inequality. Right there, we use 5 and 1 for the same reason. So we get x1 plus 6x2 on the left-hand side. So we want y1 plus y3 to be equal to 1. And we want y2 plus y3 to be equal to 6. Furthermore, I'm going to stipulate that y1, y2, and y3 need to be positive. What's this look like right here? It's a linear program. We are trying to solve for y1 plus y3 is 1, y2 plus y3 is 6, such that this thing over here is made as small as possible. That's a linear program. So we could solve, rather than having to grope around and find that 5 and 1 work, we can solve for them. There's your linear program. And that's called the dual. So you can just mechanically derive the constraints in the objective function, like I just showed you, just by adding all the constraints together multiplied by unknowns. So the variables in the new linear program are just the unknowns you multiplied the original constraints by. We know what we want the coefficients to add up to. We need to make the coefficients look like the objective function. So anyway, that becomes our program. And so if we solve that program, we can get 1900 as the minimum value.
Will the dual ever be easier to solve than the original?
Say what?
Will the dual be easier to solve than the original?
It could be. What if we took this? This could have been our original program for chocolate. I don't know how we would have come up with it directly, but if we did the dual for it, we'd be, you'd come up with that original program. Yeah.
So would it be correct to think of this as on the top we're minimizing the upper bound and on the bottom we're maximizing the lower bound?
Yeah.
And by doing those things we verify that the optimal solution is 1900?
Yeah, well, so I talked about verifying just to motivate this whole thing.
Okay.
Ultimately, our goal isn't to verify. It's just to demonstrate that so the original linear program we'll call it primal, and this is the dual to that original program. In most cases, any linear program will have a dual. And if the original is a maximization problem, the dual is a minimization problem. And, it's just two different ways of solving the same thing. Yeah.
There's only one dual, right? You can't have more than one dual.
Well, yeah. At least using this approach, you'll compute a unique dual. So there's the dual, there's the primal, and there's a solution you'll get. So if you ran the dual program through LP solve, you would get y1 is 0, y2 is 5, and y3 is 1. Now, where have we seen those coefficients 5 and 1 before? Right? That second equation up there. 5 and 1 were the coefficients we used to make that inequality work out the way we wanted it to. So our linear program solved for it, but the value of the objective is 1900. So the primal, we made the objective as big as we could subject to constraints. In the dual, we're making it as small as we can subject to constraints. Both cases, we hit the 1900. So primals have duals. And here's the property. So if a linear program has a bounded optimum, okay, sometimes the answer can be infinity if there are not enough upper bounds, then so does its dual, and the two optimum values are the same. Yeah.
So if you view this as like a convex polygon, is all you're doing just rotating it 180 degrees and then trying to...
No, you're not. It's not a. Remember, the dual was a two-dimensional problem, right? There were two kinds of chocolate, two variables. I'm sorry, the primal had two variables. The dual has three, so the dimensionality has changed. Now, let's look at the dual, the shortest path program. So that duality theorem tells us there will be a dual to this that's a minimization problem. Okay? So I'm going to multiply each of those constraints by a variable before we add them up. U, V, W, X, Y, Z. All right, that's how you compute the dual. You start by multiplying all the constraints by a variable, each constraint by a variable, and then adding them up and rearranging. Well, here I'm just rearranging. Add and collect terms, and we get that. You get this is less than or equal to that. Okay? And then where does our program come from? What do we want these variables to add up to? What do we want the sum of this to be? We want to match the objective up there. Just trying to put an upper bound on the objective. So yeah, u minus v minus x must equal 1. V plus w minus z must equal 1. We want this to turn into be a plus b plus c plus d. So this was the original objective. Okay, let's look at the dual program. We're minimizing the right-hand side of that thing. So now this is a 5-dimensional problem. Subject to the constraints to those constraints. Now, I said u minus v minus x has to be equal to 1. Why do I put greater than or equal to 1?
Because this is a minimization problem.
It's a minimization problem, so allowing them to be greater than, saying it's equal to 1 is stronger. Saying it's greater than or equal to 1 is, it would be even more impressive if we minimize that. Basically, if it's bigger, it's going to tend to make the objective function larger. So there's really no harm done. In the standard form, instead of putting those inequalities, we make it inequality. We could have left it as equals, but that's just the version we see things. So there's our program. And if you run it and solve it, that's what you get. You get the minimum is 13, and you get u, v, w, x, y, and z. You get values for those that minimize. Now, I realize that, going through this example like this, I'm doing the work and you're just watching it. It may be hard to follow the steps. But here's the spooky part. This was just derived mathematically, and yet there's a physical interpretation for this. We can look at those variables and look at that objective and say, yes, that's a way we could have conceived of solving the problem in the first place. Basically, by computing the dual, we have come up with a new algorithm. We've mathematically derived an algorithm for solving the problem. So what physical interpretation can you give to those variables? And to that, what exactly are we minimizing? Look at the coefficients up there in the objective. What are they? Yeah,
Are those the weights of the edges?
those, turns out, those are the weights of the edges in the original graph. So somehow they've shown up in the dual. And we're trying to minimize 5, which is the weight of one of the edges, times v, plus w, which, 1, which is the weight of another edges, times w, plus 3, and so on. So yeah,
So we're trying to minimize the number of times we use the heaviest edges?
exactly. Think of v, w, x, y, and z as the number of times. Suppose you create the shortest path tree, said it right, and you start at A and you go to B. And then you start at A and you go to C. And then you start at A and you go to D. How many times do you cross each edge? So if you remember that tree, how many times would you follow the edge from A to B?
V times?
Well, the actual tree, well, I think I need to show you the actual tree. Okay? So here we are. So notice, you've got 5, 3, 1, 2, 4 there. They show up there. Think of x as the number of times you're going to follow that edge from A to C as you go from A to every other vertex. Okay? Why does 3 make, well, what is x?
The number of times we traverse A to C in this
So-
path?
Okay, let's look at it differently. Y here. Y is, this edge corresponds to y. And you see 4 times y shows up. How many times do we follow that edge right there in the minimum spanning tree?
None.
In the shortest path tree? None. And so, yes, y is 0. Do we ever follow the edge from A to B? No. So v turned out to be 0. Okay? So, now, suppose you start at A and you follow the shortest path to C. You traversed edge x once, right? Now, you start at A and go to B. You traversed it again, that's 2. Now you start at A, you go to D. 3. 3.
What's U then?
What's U?
Is it just A going to A?
Yeah.
Yeah.
Basically, how many times did you go from A to A? You know, we're sort of pushing it.
Leave A. Like,
Yeah, how many times do you leave A? But the cool thing is that we computed the dual, came up with this, and yet you can look at it and say, yeah, that makes sense. We are, it's one way to think about the shortest path problem is you let the variables represent the total number of times you traverse each edge. You're trying to minimize that sum subject to what constraints? How do the constraints make sense? What does u minus v minus x? Well, let's do the bottom one. What does z minus y is greater than or equal to 1? Let's change it back to the way they were originally. Z minus y equals 1. Okay? Why does that have to be the constraint? Or what does that constraint mean? Yeah?
Does that mean we're entering D once? Or like, in total sum, you can't have more going out than coming in?
Yeah. So if z minus y equals 0, that would mean that every time you entered D, you left it. Okay? But when we say z minus y equals 1, we're saying you have to enter D one more time than you leave it. So one time, one of the paths has to stay in D, which makes sense. So these constraints are saying that for every vertex, well, let's look at u minus v minus x. Okay. Oh, yeah, that's the A one. Let's do v plus w minus z. What's that saying? What's v plus w?
how many times you enter B?
That's how many times you enter B. Z is how many times you leave it. So it's just saying that every time you enter B, you must leave it, except once. So looking at all the paths in the shortest path tree, one of the paths has to stop at B. Right? Because one of the paths has to be the path from A to B. Any other time you enter B, you have to leave it to go somewhere else. So that's what those constraints are seeing. It's sort of like the oil problem again.
new constraint that says like u plus v plus w plus x plus y plus z must be 2 times the number of vertices minus 1?
I'd have to think about that. But I remember when I first encountered this, I was preparing these slides and I was working at my computer and I came up with the dual and I says, how could I interpret that? And I was floored. It just seems spooky to me. That's the word I still use, that it could, what ought to be sort of an artificial creation actually have a direct physical connection. And it's not like, I don't think we would naturally come up with this way of describing the problem. I think the way we did it first is. But you can at least sort of see why this makes sense. So it's not just a mathematical abstraction. The dual actually gives us some additional insight on the problem. Yeah.
Does the dual always have one more variable than the primal?
No, the dual doesn't always have one more variable because, let's let this be the primal. So if we compute the dual, we go back to our original problem, and it...
Or would we end up with like an even bigger problem?
I think we go back to the original problem. Well, I have to try it and see. Okay?
And then when the dual, like some of the solutions are 0, can you like just move it or?
Some of the solutions are 0.
Yeah, like v is equal to 0 or y is equal to 0, and then if you go back.
Well, that's just saying those edges aren't used.
That's in a solution.
I mean, in retrospect, you can see ways to simplify the problem. If you solve the problem, you can tell what constraints didn't matter and simplify it, but you don't know that until you solve the problem. Okay? All right, let's take a break and we'll look at something different.
or?
That was like,
Good.
never done any of this.
All right, let's get started again. Okay, so far we've been using our linear programming solver as a black box, and we're pretty much contained in that. I just want to say a little bit about how solving works. So the simplex algorithm, which is what I've been just, when I sort of tried to motivate a little bit about how linear programming solving works, that's the simplex algorithm. So it was discovered in 1947. In the worst case, it takes exponential time, but in practice, it works really well. The exponential case doesn't come up, typically. It took until 1979, 32 years, it was a Russian researcher that developed what's called the ellipsoid algorithm. It runs in polynomial time in the worst case. So that's good. But in practice, it performs poorly. High constants, I guess. And then in 1984, there was a student, I believe at UC Berkeley, that came up with a polynomial time algorithm that works well in practice. And that's called the interior point method. And these two methods, simplex and interior point, have been improved since then, and they're competitors. So it's not like one is vastly better than the other. The existence of each spurred ingredients in the other.
Is that a duplex algorithm too?
Duplex? I imagine there's more than these three. But anyway, it's been an area of development. Now, the key idea behind the simplex algorithm, we've seen this graph before. So this is our chocolate program. The pink is the feasible region. And what was this line right here? Yeah.
Objective function.
Okay, that's a graph of the equation x plus 6y equals something. I forget what it equals. Like right here, it crosses there. At this point on the line, well, anyway, all along this line, 6 plus xy has a particular value. And as you move this line up, say they put a parallel line up here, every point on that line in the pink region would have the same value, but it'd be a higher value. And so you can think of solving the program as one of pushing this line up until it touches the last point in the pink region. And that's the solution. And I observed at the time that if you do that, what's the last point this line touches?
300, 100.
The vertex up there at 300, 100, which is the solution. It touches that point, and then it leaves the feasible region. Okay? So the way the simplex algorithm works is it starts at the origin, and maybe the feasible region is such that there isn't a vertex at the origin, but you can always translate the coordinate system and get something at the origin. So you evaluate the objective there. So let me back up. One thing you could do is just evaluate the objective at every vertex and take the max. What would be the problem with that?
It's a lot of vertices.
There can be a lot of vertices. Not in this case, but if you have lots of variables, a high dimensionality, lots of constraints, you can have lots and lots of vertices. You don't want to look at all of them if you can avoid it. So Simplex uses a hill climbing algorithm. It evaluates at the origin, and then it looks at all the neighboring vertices, the one that you can reach via an edge. And it takes the largest. And it goes there, it looks around, goes to the largest neighbor. It just keeps going to the largest neighbors until all the neighbors are smaller. Now, sometimes hill climbing can fail because you just reach a local maximum. But it always works with simplex. Right? You don't ever reach a local maximum from which you can't escape, even though it's not the ultimate answer. It's always increasing until you get there. You see that here. It goes 0, 1800, 1900 if you go that way. It goes 0, 200, 1400, 1900 that way. And you can see sort of why it works, because as you mush this line up, the line is it's first going to touch that one. And then, well, first it'll touch this one, where it's 200. It'll touch that point where it's 14, then that one last. Physically, if you just imagine this thing leaving. And so that's what all Simplex does. And to make it fast, you've got to make it efficient, calculate what the neighbors are and what the value of the objective is at them. And that's where the algorithm's been improved over the years. But fundamentally, it's just a simple hill climbing algorithm. Yeah?
Does the hill climbing avoid local maxima because our polygon is
It's convex. Yeah.
How do you find these corners? Is it from the constraints? Or how do you derive from the constraints to the corners?
Yeah, well, see, that's figuring out what the corners are is at the heart of the algorithm, doing that efficiently. There's a tiny sketch of it in your book, and but beyond that, what I just care about for purposes of the class that you understand it's a hill climbing algorithm, and that calculating where the corners are efficiently is certainly key, but I'm not going to go into that. Okay. Now, we've talked about the feasible region. I just want to talk about types of feasible regions because I think there'll be a problem on the next assignment that involves it. So this is what you call a bounded feasible region, finite size. Okay? This is an infeasible region, or not. A program is infeasible. We say this program here is infeasible because the feasible region is empty. So if you've got a bounded region like that, you're always going to be able to find the optimum. Here, no solution exists because there is no feasible region. Yeah.
Is that because your constraints are inconsistent?
Yeah, it's just over-constrained.
Okay.
Yeah, this is just an artificial set of constraints, but you know, it's just an over-constrained problem, and so forget about optimizing it. There's no solution at all that satisfies all the constraints. Or you can have an unbounded feasible region. Now, even if it's unbounded, you might have an optimal solution. Does this one right here? This is unbounded because it goes infinitely up in that direction to the top of the slide. Does it have an optimal solution nonetheless?
X equals 200 and Y equals alpha null.
Does it have a solution from the integers, from the real numbers? No. Because this just increases without bound. Okay? On the other hand, what about that one? What did I do?
You minimize instead of maximizing.
Okay.
Oh.
Yeah, so I'm minimizing it.
Oh yeah, that does.
Okay, so now the solution is going to be, the solution is always at a vertex. If there's no vertices, you're out of luck. But in this case, there's two vertices, and one of them is the minimum. Not in there. So you can have bounded finite feasible region, there's guaranteed to be an optimal solution. You can have a completely infeasible program, there is no solution. You can have an unbounded feasible region, and it may or may not have a solution. It just depends on the details. Okay? All right. All right, that brings us to our last major topic of the semester, in which only 2 weeks or 3 weeks? 3 weeks. Get close. And the last major topic is not the traveling salesman problem. It's just the first example we'll look at. So the traveling salesman problem, famous problem. You got a graph. We'll assume it's undirected here. We want to find the shortest, simplest cycle that visits every vertex exactly once, returning to its starting place. Now, that's the traveling salesman problem. It's an optimization problem. You're trying to find the shortest cycle. Okay, you're not allowed to revisit a vertex after you've left it. You go back to the beginning point. There's a related problem called the Hamiltonian cycle problem, and that is just to find a cycle. Forget the weights. So, what will be a solution to the Hamiltonian cycle problem here? Yeah?
A, B, E, C, D, F, B.
I guess, but it's easier to see just A, B, C, D, F, E, A, right? goes around the outside. But there's lots of solutions. There's so many edges. You know, A, B, F, C. Well, I think I got stuck.
A, B, F,
A,
D, C,
A, B, F, D, C,
E,
A.
A.
You know, there are various ways to do it. So the Hamiltonian cycle problem is that, just finding a cycle. The traveling salesman problem is the Hamiltonian cycle problem, except you're trying to find the shortest Hamiltonian cycle, the smallest. Okay, and there is a solution. That turns out, you'd have to stare at the graph a while and figure it out, but that is the shortest Hamiltonian cycle for that graph. Okay. Now, we're going to define what's called a search problem. We'll come back to this example shortly. So in a search problem, we're given an instance I that describes the problem at hand, and we're asked to find a solution, an output that satisfies the specification. And that sounds like a lot of things we do. But the other requirement we're going to make is that any proposed solution must be checkable in polynomial time. So if someone gives you a solution to the problem, so let's say you give them the problem instance, namely a graph, and you ask them to find a solution, namely a set of edges that satisfies the problem. It's called a search problem if any proposed solution can be checked in polynomial time. So think about the shortest path problem. Is that a search problem? Yeah?
Yes, because it's solvable in polynomial time and thus
Right.
it can be checked in
So if it's solvable in polynomial time, it's checkable because you can just solve it. Checking is just amounts to solving. Is a traveling salesman problem a search problem?
Yeah.
It's a little hard to see. Why do you say yeah?
You're searching for the smallest Hamiltonian cycle.
All right, so if someone gives you back a Hamiltonian cycle and asserts this is the smallest, how do you check? How do you verify that it is the smallest?
You have to solve again.
It's incomplete, so that means you should be able to check it, right? In polynomial time, not.
Well, I'm saying, tell me how to check it fast. Yeah?
If you already have basically a mid-weight, you could just, you'd still technically have to check every path, but as soon as you hit a weight that was greater than your min, you could move on to the next one.
Okay, so that's the kind of thing I'm looking for, is how you would do the checking. But it's a little unclear exactly how you would check fast if it is the smallest. Now, let's take it different. What if instead we asked, just give me a cycle, solve the Hamiltonian cycle problem? Would that be easy to check?
Yes.
Yeah, it's easy to take the solution of the Hamiltonian cycle problem. What do you have to check? That you visit every vertex, and you return to where you started, and you don't visit any vertices twice. That's, yes, easy to check. You just trace through the graph, 3 edges, make sure it all works. So it's easy to see that's a search problem. It's harder to see that the traveling salesman problem is a search problem. And in fact, we're not going to classify it as a search problem. We're going to classify it as an optimization problem, but we'll see it doesn't make much difference. Okay. That's what I was just saying. I don't know how to efficiently check that it's optimal. Well, actually I do, but it's not all that clear. So that's what so this is what we just talked about. It's easy to see the Hamiltonian cycle problem as a search problem. It's harder to see the traveling salesman is. Okay, now this is the game we're going to play for the rest of the semester. Polynomial good, exponential bad. And it's kind of ironic because we spent the last 12 weeks saying, n squared bad, n log n good. We were taking all these algorithms we studied ran in polynomial time, and we were struggling to turn n squared algorithms to n log n, or n log n to linear. And now I'm about to say, okay, let's not be so picky. We'll say any polynomial time algorithm we're going to call that good. Any exponential algorithm we're going to call bad. And we're no longer going to try to distinguish between degrees of goodness. The distinction between n squared and n cubed, so what? They're both polynomial. Now, is that a reasonable thing to do? So what does it mean when I say this problem has a polynomial time algorithm? What am I saying? Yeah?
The upper bound is always n to the c, where c is some real number, or some,
Okay. It means that the upper bound on the algorithm is a polynomial. In the worst case, it can still be solved in polynomial time. What does it say if I say that all known algorithms require exponential time? Yeah?
We haven't found a polynomial time one yet?
Well, that is true.
Is
It means we haven't found a polynomial time one yet. It means all the known algorithms, there's some case that requires exponential time.
well, what about factorial time? Is that still
Well, exponential time or worse. But the lower, there's some case that has a lower bound that's exponential. Okay, so that's what we just said. If it's algorithm, if we say a polynomial, that an algorithm is polynomial time, then it's we're saying it's O of n to the c for some constant c. And if we're saying that all known algorithms require exponential time, we're saying that each algorithm has a worst case of c to the n. I mean, the worst case for the algorithm requires c.
best case?
Best case. No, it's exponential in any case. Well, this is a lower bound on the algorithm. That doesn't mean every case requires exponential time. It means some case requires exponential time. Polynomial time good, exponential time bad. But why should this be considered good and that be considered bad? In practice, you would certainly prefer that algorithm over that one. This is massive. This is tiny. Now, it turns out if you make n big enough, yes, this will eventually overtake that in terms of time. It'll take longer for this than that. But, you know, I could add many more zeros here and many more zeros there. Where do we get off saying polynomial bad, polynomial good, exponential bad? What do you think? Yeah?
Is it because we want to find solutions for arbitrary sized problems?
Well, that's certainly the game we've been playing all along. But that's not, there's a different way of looking at it, yeah.
On average, the polynomial time algorithms can perform better?
Well, no, if we really had these algorithms on reasonably sized problems, the exponential algorithm would outperform the polynomial, no doubt. So what's going on? Why do people get excited when a polynomial time algorithm is discovered? Yeah?
Maybe people saying the polynomial solution is solvable and the exponential is unsolvable.
Well, no, that's no.
That's because you can map some problems to a problem you already solved in polynomial time?
That's closer.
So if you solve one of the exponential problems in polynomial time, then all of them can be solved in polynomial time?
Well, yeah, that's a different thing. Yep.
Is it because if it's solvable in polynomial time, then it's checkable in polynomial time? Not really.
Well, that's related to what he said, actually, but that's going deeper right now than I want to go. Yeah.
Because you improve the constant later?
He said because you can improve the constant later. And actually, it's not the constant that matters here. What matters is that. Here's the bottom line. When a problem, suppose there's some problem out there that the best known solutions have always required exponential time. And then someone thinks about it and comes up with a polynomial time algorithm for it. What that is called is a breakthrough. Someone has, typically if it's exponential, you're just trying all the possibilities. So we don't know anything better to do than try all the possibilities. Then someday someone discovers a better way. They've discovered a way of looking at the problem that no one ever thought of. And they've come up with a radically different approach to solving it. So suppose this breakthrough occurs, but the breakthrough algorithm is still too slow. What do you think happens next? Yeah?
Everybody in the world tries looking at it that way and
Yes.
seeing what the best way they can do it.
Right. All the researchers in the world read that paper, and they say, gosh, this guy had a breakthrough. I want to understand the breakthrough. And they suddenly got this new idea, this new technique, and they try to improve on it, or they start applying it to different problems. And what generally happens is the algorithm gets improved rapidly. Not always, but like the AKS algorithm for checking the deterministic algorithm for primality started out life as an end of the 12th algorithm. It was rapidly improved into the 6th when other people looked at it and improved on the ideas of the original. So the idea is if an algorithm, if a problem, first of all, this just doesn't happen in practice. But things aren't that wacky. When the best algorithm you have is exponential, you don't really know how to attack it. Once you discover a polynomial time, now you have a way to attack it, and that can be followed up and improved. So, just to give you a heads up, what we're going to be studying now is a class of problems called the NP-complete problems, and they have the following properties. First of all, they're problems such as the traveling salesman problem that people would like to solve. Second of all, for none of them have a polynomial time algorithm been discovered. And furthermore, if even one of them, and there are thousands, tens of thousands of these problems, if one of them could be solved in polynomial time, all of them could. So all it would take is a single breakthrough on one of these problems, and that breakthrough could be applied to all of these. It would be earth-shattering if the fast algorithm were discovered. So we're going to try to understand what I just said. So that's not today.